Uh, so, Good morning, everyone. I'm Boon Sian, and today I will introduce the topic about index theory. Index theory is a method that provides global information about the fish product, and it enables us to answer questions such as is there a closed trajectory always encircle a fixed point? And if so, what types of fixed points are allowed, and what types of fixed points can coalesce in the verifications? The method also yields information about trajectories near the higher order fixed points. And lastly, we can sometimes use index arguments to rule out the possibility of closed orbits in certain parts of the phase plane. However, in this presentation, we will only cover until the part about index over point. So suppose that x dot equals to fx is a smooth vector field on the phase plane, and consider a closed curve C as below. And that is not necessarily a trajectory, is simple and does not pass through any fixed point of the system. Then at each point x on C, the vector field x dot makes a well-defined angle phi with the positive x-axis. So we can see phi is actually the arctangent of y naught over x naught, y dot over x dot. The angle phi must change continuously as the vector field is smooth and as x moves counterclockwise around C. And we see that the phi will returns to the original direction when x returns to its starting point. And then we let the close bracket of phi to be the net change in phi over one counterclockwise lap around C. So when x moves one counterclockwise lap, the close bracket of phi will denote the net change. And then the index of a closed curve will be the net change over radian divided by 2 pi. So IC would be the net number of counterclockwise revolutions made by the vector field as x moves one counterclockwise lap around the closed curve. And then below will be some examples on how to calculate the index. So as can be seen, first we will index each of the point 1, 2, 3 until 8 to see how the angle phi will change when the index x moves. And then we find that 1, 2, 3 until 8 is a counterclockwise. So the angle changes is 2 pi, which means that the index is 1. And the same for the next, we look at the index of the vectors, and then we have a clockwise direction. So it's negative 2 pi because it is clockwise, so it's negative. So we obtained negative 1. And next, we look at the index 1, 2, 3, and then 4, 5, 6, 7, 8, 9. So from 1, 2 to 3 is clockwise, so we get negative pi. And then from 3, 4, 5, 6, 7, we get one rotation, which is 2 pi. And then from 7, 8, 9, we get a positive, we get a clockwise, which is negative, so we get 0. So the index is 0. And for the last part, we have 1, 2, 3, 4 is one rotation, and 5, 6, 7 is another 2 pi, which is 4 pi. So we have the index is 2. And next we'll discuss about the properties of the index. So if a closed curve can be deformed to another closed curve without passing through any fixed point, then the index are the same. And then if the C does not enclose any fixed points, then the index is 0. And if we reverse the directions of the arrow, the index is unchanged. And then if the closed curve C is a trajectory, then the index is 1. So we only prove the part 3 and part 2. To prove part 2, we shrink the C to a teeny circle while fixing the index. This is by part 1, the index will not change, and then phi is essentially constant because we know that the closed bracket of phi would be integer value, or I mean the integer multiple of 2 pi, and the vector field is moved, means that integer value function needs to be continuous, means that it must be constant. So it does not change, so the index will be 0. And to prove part 3, we notice that if we reflect, we change the direction of the arrows, it's actually the same as we rotate each of the vectors by pi radians. So the index remains. And then we will discuss about index of a point. The index would be defined as I, where C is any closed curve that imposes only that fixed point. So by property 1, IC is independent of C. And next, we will discuss about the index of stable and unstable knot. So the vector field near a stable knot looks like the vector field of the first example. It is a stable knot, and know that every arrow will point towards the stable knot. So the index will be similar to this value is 1. And then positive 1. Next, the index of unstable knot. First, we know that to obtain unstable knot, we reverse the direction of the stable knot so that it will point outwards. So to obtain an unstable knot. And then property 3 we discussed just now. Only the arrows are reversed, means that the index is unchanged, so the index is also positive 1. So here we discuss the index of a stable and unstable knot, and here is the end of my presentation. Thank you.